Greetings dear students, I am Archana from Department of Biomedical Engineering, PVR 18 Narsapur. I am working as an assistant professor here. So today I am going to explain you about classifications of the transducers and various characteristics that transducers has, and also we'll see the generalized medical instrumentation system. So what is a transducer? We actually see them every day in our life. Like if you go to a fan, it converts electrical to some motion, right? It rotates, right, when it's switched on. So this transduction happens because of a transducer. So a transducer is a device that converts one form of energy into another form of energy. So as it is depicted here, we will have a transducer, then one form of energy. It can be a light, it can be electricity, or it can be any other form of energy that can be given. So when we apply it to a transducer, it gives you as an output in another form. For example, take a speaker. We all know the speaker, right? So speaker, it generally takes an electrical signal and converts it into a sound. So now we'll see sensor. There is generally a confusion where transducer and sensor works as the same, and there is a basic differentiation between a sensor and a transducer. These days we use it as a synonyms, but it is not. So a sensor is a device that detects and responds to some type of input from the physical environment. Like you can give any light, any physical phenomena as the input to a sensor. It will convert it into a perceptible output, generally as an electrical signal. So for this, we can take an example as microphone. A microphone takes in sound, which is a physical phenomena, right? Which is a physical quantity. A sound is a physical quantity. This has been converting into a electrical signal. So this is how a sensor works. But wherein is a transducer, it converts one form into the other form. It is not mandatory. Electrical signal has to be produced as the output of a transducer. So now we'll see the classifications of the transducer. So classification is based on various characteristics. Like the first one is based on the power sources that are being used for the transducer. So it can be an active transducer or it can be a passive transducer. As we have seen in active transducers, so here you have an active transducer. For this you'll give an input, right? Any physical phenomena, you'll give an input to it, you'll get an output which is in the electrical form. Okay. So here this is a self-generating transducer. It does not require any kind of assistance to get it converted into a electrical form. So wherein we have passive transducers. Passive transducers require a external source to excite them so that it will give you output in an electrical form or any known value or any known perceptible form. So for this passive transducer, for passive transducers, you need to give an external source as excitation. So these are not self-generating transducers and they require external source to give electrical form of output. So next is based upon the output conversion. So we have different types like primary transducers, secondary transducers, analog transducers, digital transducers, and inverse transducers. So now we'll see what is a primary transducers. I hope everyone here might know Gordon tube, right? So Gordon tube is nothing for, it can be used for a pressure measurement. It is kind of a C-shaped structure where it is connected to a pulley, then it is connected to the core of an LVDT, which has a excitation source coming in, and you have a series opposition circuit here where you measure the voltage here. So when I apply some pressure to it, there is the deformation that is happening in this tube, right? So it causes some displacement. It causes some displacement. When this displacement happens, it either pulls in this, it pulls in the pulley which we have connected to the core, and with this the movement of this core of an LVDT, an electrical output is obtained, right? Here we will get the V out. So by this, the displacement part, from the pressure to displacement part, we consider it as a primary transducer. So herein we are focusing on how a physical phenomena is again converted to a displacement, right? Pressure is a physical phenomena which is converted into a displacement. So here we can see there is some mechanical action that is taking place. Now this mechanical action, because of this mechanical action, we have the movement in the core of the LVDT, that is linear variable differential transformer, and we have the changes in the output, right? So here these LVDT acts as a secondary transducer. Now we have analog transducers. Analog transducers are nothing but we have seen it in our day-to-day life, like where you'll get an analog signal. So what is analog transducer? With this, output of analog transducer changes accordingly as a function of time. So usually we get some kind of waves as output of these transducers. So you can take your CROs where you have a sine wave that is being displayed on a CRO, can be considered as your analog transducers. Now we have digital transducers. Digital transducers are the one which have a specified value. For example, take your thermometer, a digital thermometer. So when it senses the heat temperature of the body, it gives the output in the form of centigrades, right? So that is considered as your digital transducers. It has a predefined value set in there, and it gives output in that values itself. Now we have inverse transducers. Inverse transducers can be better understood by the most famous material, that is piezoelectric crystal. We all know, right? When a piezoelectric crystal is subjected to a mechanical stress or mechanical vibrations, it is converted into there is a change across the voltage on the surface of the piezoelectric crystal, and we take that voltage as an output. So this inverse can also be happen in the transducer, in the piezoelectric crystal, right? It can convert mechanical energy to a electrical energy, or electrical energy to the mechanical energy. So this is known as inverse transducer. I told you transducer is a form of, it converts one form of energy to another form of energy. So the reverse is of inverse transducer. Whatever the converted energy is there is converted back to the another energy. So based on the principle of operations, this can be divided as photovoltaic transducers, photoconductors, piezoelectric transducers, electromechanical transducers, thermoelectric transducers. So as we know, solar cell, photovoltaic transducers, you can take it as a solar cell, right? So they actually take in energy, they take in light, they causes some variation on the surface of the material that is being taken, and a voltage is proportionally changed according to the light, or these voltage can be directly taken as an output of these transducers. Next we have photoconductors. Photoconductors, the main difference between photovoltaic cell and a photoconductor transducers is photovoltaic cells, irrespective of the intensity that is being applied, there is some change according to the voltage that is obtained at the output. Whereas in photoconductors like photosensors and phototransistors we see in lab, they change their output based on the intensity that is being given, right? When we do photodiode experiment in our labs, we find, right, we take the experiments like at different light intensities. So with the photodiodes, we take different light intensities, and we measure them. Measure the voltage or current levels. So piezoelectrical transducers, as I have mentioned before, it is an inverse transducer. It can convert from mechanical to electrical and from electrical to mechanical. Next we have electromechanical transducers. Electromechanical transducers are that they given some mechanical output when subjected to electricity. For example, you can take in as your fan. When you switch on, when you supply a current to it, when you switch on, it gives you a motion, right? So here electricity has been converted into some physical phenomena. Some physical quantity it has been converted. Next we have thermoelectric transducers. Thermoelectric transducers are sensitive to temperature. So based on the temperature, you'll get a electrical output. So for example, you can take thermocouple. So thermocouple is a temperature sensitive transducer wherein two dissimilar metals are joined together, which forms two junctions. Because of the two different temperatures at these two junctions causes an electricity to be induced in that circuit. So here it is because of the temperature gradient along that homogeneous wire, we will have a electricity as a output. Electrical parameters like it can be a current, it can be a voltage that can be achieved from your thermoelectric transducers. Now based on the quantity to be measured, so what is that quantity you want to measure will have different. If for suppose you want to measure pressure, how do? You go for a pressure transducer. For temperature measurement, you'll go for a temperature transducer. So if you want to go for any kind of echo measuring things or distance, object detection, you go for ultrasonic transducers. If you want to find displacements, you go for displacement transducers. If you have inductive induction, principle of induction. If you have principle of induction, you go for inductive transducers, and you have resistive transducers. So whatever the quantity that you want to measure from a system can be have different types of transducers. So for example, if you go for a pressure transducer, you want to measure pressure of anything. So you will go for a pressure transducer. Pressure transducer is nothing but it takes in pressure as the input and gives you electrical output. Then you have temperature transducers. These temperature transducers can be thermoresistive or thermoelectric. So if you go for thermoresistive transducers, you have thermistors and RTD. So the resistance of the material that is being used in these devices like thermistor and RTD will be varying according to the temperature that is being given. They may have positive temperature coefficients or negative temperature coefficients. And thermoelectric is the best example of thermocouple. Ultrasound transducers, when you subject it to electrical signal, it provides you a vibration. When these vibrations go and when this vibration touches the human tissues, it will send back them as a electrical signal, which is then converted to a perceptible output, that is imaging modality. So inductive transducers, it can be of LVDT. LVDT works on the principle of mutual inductance. So inductive transducer will be your LVDT. With this LVDT, we have a movable core. When it is excited, this is the primary, this is secondary 1, this is the secondary 2. Secondary 1 and 2 are connected in series opposition. So when the core is at the center, the output would be S1. So for inductive transducers, so most of these inductive transducers works on the principle of inductance, mutual inductance. So based on the change of the mutual inductance, there is a proportional output voltage that has been obtained from the transducers. Then you have resistive transducers. For resistive transducers, you can take as simple as that as potentiometers or strain gauge. Strain gauge, when we apply a force or pressure onto a material, the electrical resistance will be changed. The electrical resistance of this material change. So we cannot use this electrical resistance, or we do not have any kind of we don't have any means to measure this electrical resistance. Hence we connect the strain gauge as a unknown arm in a Wheatstone bridge. As an unknown arm in the Wheatstone bridge. Unknown arm in the Wheatstone bridge. So resistive transducers is like its electrical resistance of that material will be changed when it is subjected to any physical quantity or electrical quantity that is given as an input, and we will have the changes in resistance of that material. So now we'll see the characteristics of these transducers. We have static characteristics and also the dynamic characteristics. Static characteristics does not change with the time, or they are stable during the operation, and dynamic characteristics are vulnerable to the change with the time. So static characteristics, we have accuracy. Accuracy is nothing but how close is your measured value to the true value. True value is the reading that you are expected to come, the expected outcome from the transducer, and measured value is what do you get when you use that transducer. For example, I have a BP sphygmomanometer. For example, I have a sphygmomanometer and I want its output as 120/80. But when I am measuring with that instrument, I have somewhere 110/70. So here I have the difference of 10 above and 10 below, right? 10 in the denominator and 10 in the numerator. So how close is your output that is measured to the true value is given by accuracy. That is, measured value minus true value by true value. So this gives you the accuracy. Linearity is that characteristics where for the input that is you are giving, the output should change linearly. So for example, let me take RTD. RTD is resistance temperature detector. So we will plot a graph to the RTD between temperature and the resistance. Temperature and the resistance, or resistance per meter, it can be a resistivity. So when you draw it, you'll have a linear scale. That is, for every degree change in the input, you'll have a linearly changing output there. So this is known as your linearity. Repeatability is that characteristic of an instrument where it has to give the same reading when it is measured under the same environmental conditions. So for example, I give 2 as an input to my transducer for the first time where environmental conditions are normal. So it gives me some output as 4. So whenever I give this 2 under same conditions multiple times, my system has to give me the output as 4. Okay. Now we have stability. Stability is that characteristics of a system where how stable the output of your system is. Is it providing, for example, I am measuring some voltage from the device. So for the first time when I am measuring, it got me 2 volts. So when I am using a voltmeter, it showed me a 2 volts as a output. Rather, while I am noting this 2 volts, it showed me as 2.1. Then rather, it showed me 2.2. In the same time, for one reading, if you have many different values or your voltmeter is very sensitive and it is giving you a very kind of different values for one measurement. So we say the system is not stable. For a set of time, so for a set of time period, once the input is being taken, the output should maintain at a constant value for some period of time until the input is removed. Next, we have sensitivity. Sensitivity is the ratio of change in output to the change in input. Change in output to the change in input. So, how is your transducer or a system is responding to the input that you have given? So, what is the changes that you can observe in the output when input is changed? Can be known with the sensitivity of the instrument. Now, we have precision. Precision gives you the measure of reproducibility of the system. Or transducer. So under the same condition, I said repeatability is under the same conditions, it should give you the same output. So the precision is how many times the degree of closeness to the repeatability is being found by the precision of that instrument. Now we'll see what is range and what is span. So what does a range mean? For example, I have a transducer A and I have to put it in a boiler tanker which is of so and so X length, and it has a upper maximum limit of fluid filled with till 20 meters, and from the bottom it is starting at 2 meters. Okay, the liquid is being filled between 2 meters and 20 minutes. Now I want to check whether my transducers be able to reach the upper limit of the tank and the lower limit of that tank. So range is nothing but the limits of the transducer that is being used or the system that is being used. Now span. Span is nothing but, now for example, we have taken here 2 meters and 20 meters as the minimum and maximum ranges of the transducer that can be used, right? Now the span tells you what is the actual movement of that transducer or the system that is being used. For example, here maximum range is 20 meters and minimum range is 2 meters. So 20 minus 2 will give you 18 meters. The span of this transducer A is 18 meters. Okay. Now resolution. Now we will see resolution. Resolution and sensitivity might be seeming same for you, because we say sensitivity as a change in output to the change in input, right? So here the resolution only concentrates on the input variation, how the system is sensitive to the input that is given. So for example, I have some kind of potentiometer type of a device with me, and I wanted to measure, for example, take a capacitive transducer, the rotational one. If you want to measure the rotation of the rotation using that capacitive transducer, wherein for a 0 degree centigrade, so you will be having a semicircle kind of thing where from it will have the readings from 0 degrees to 180 degrees, and your transducer is capacitive transducer is connected to this scale, and your transducer is connected to this scale. Now when you rotate this to 0 degrees to the 180 degrees, it will give you some kind of relevant values that are expected as their outcomes, right? So now resolution is, if I give at 0 degrees, the output should be somewhere around 0, right? So if I make my transducer to go for 0.1, this shifting from 0 to 0.1 is nothing but your resolution. So this 0.1 change that is happening because of 0.1 change in the output, right? This is your resolution. The ability of the system to respond to the input that is very minute is known as your resolution. Now we'll see dynamic characteristics. Dynamic characteristics, we have dynamic error. Dynamic error is nothing but, so we know that error is something that is between measured value minus true value, right? Now dynamic error is nothing but, we know that error is measured value minus true value. Now dynamic error, so dynamic characteristics itself, it says it changes rapidly with the time. It changes accordingly time. So dynamic error is change with respect to time, right? Whatever we have the change because of the time in the measured value, and whatever the change we have because of the time in the true value is considered as your dynamic error. Okay. Now we have fidelity. Fidelity is that characteristics of a system where how a system is performing for different inputs. Now we have speed of response. So how far according to, for example, at 2 seconds, in the span of 2 seconds, for example, in the span of 2 seconds, how my input and output are changing accordingly with time. Now we have something called lag. So as I said, speed of response is the time that is being taken between the input and output change accordingly with the time, right? So lag is something, what is the type of difference we have from the input to the output, what is the lag that we have, that what is the delay that we have, that is the characteristics where we can get from the lag. It can be of two types. Lag can be of two types. One is measurement delay. One is measurement delay and another is retardation type. So here retardation type means the system is okay, that it is giving, like it is responding to the system with the input changes in the input. The system is able to respond to the input changes and its output is also changing accordingly. Now measurement delay. Measurement delay is nothing but there is a dead time between the output changing when the input is changed. Okay. Measurement delay has kind of dead time. So your system will not respond as soon as the input is being changed. It takes some time and then it shows you in your output. So for this you can take example as your thermometer. So whenever you put in the thermometer, it takes your delay gap of 1 minute, right? At least 1 minute you need to put thermometer on yourself so that you will get a reading, right? So this 1 minute is considered as the dead time. Now we'll see where these transducers can be used. So first thing is generalized medical instrumentation system. So this is a basic diagram for every medical system. More or less every concepts will be, so every device will be of using of these devices. So here we have measure end. So that is subject here. Now these sometimes we might give kind of electric, light, infrared, mechanical or ultrasounds to the human body so that we will get the output. For example, ultrasound, as I was discussing earlier, I've mentioned you ultrasonic transducers, right? So there I have told you first we'll excite the transducer with the electrical source, then these transducer will send the vibrations into the human body. So that human body, whatever the vibrations that are entering can be given to this measure end. Then the signals is being picked up by the sensor or the transducers. I've already told you this is where we are concentrating today, that is sensor or a transducer. Sensor is used to convert one form of energy to electrical signal, whereas transducers can be convert one form of energy to another form of energy. So as I told you, we are discussing about the medical instrumentation system. All medical signals, all physiological signals are very low in amplitude, and for that matter we can take any general purpose instrumentation system also where low amplitude signals are there, where their signal amplification has to be done. We have a signal conditioning circuit. With this signal conditioning circuit, we amplify the signal according to our output based, we amplify the signals according to our interest, like how we have to get our output. Then we do some kind of signal processing, then we will give it to any perceptible outputs, like you can give for alarms, you can go for a display, whatever you get in as a display, whether it can show you images or the numbers or the waveforms on the screens, or else we can go for data storage, we store the data for some reasons. If you want to work on for the data for the future references, we go for data storage. And sometimes we go for data transmissions. Data transmission is like you can take your satellite things as an example for data transmission, or you can take packs in the hospital as your data transmissions, or you can go for data recording. So with this, I complete the classification, characteristics, and where these transducers can be used in a generalized medical instrumentation system. Thank you.
Like, share and subscribe. Hit the bell icon for more updates.